Our next talk is Randy Sargent joins us as a visiting faculty member from Carnegie Mellon. He is a senior systems scientist there and part of their research faculty. But today he's going to tell you about the Gigapan Time Machine project, which just launched earlier this week. So, Randy?
Well, welcome everyone, and thanks for being here for my talk. I'd like to talk about Explorable time series imagery. And let me first give a bit of credit to three teams I've been very proud to be part of now, the most recent being Google, the Create Lab at Carnegie Mellon University, and the Intelligent Robotics Group at the NASA Ames Research Center have all done the primary work that you're going to see here today. First, let me talk a little bit about what's important about what I'm going to show you. So I want to talk about exploration and mapping. Turns out humans are really good at spatial information. We have this amazing three-level system, mechanical system hooked up to our highest bandwidth sensors. So we have eyes can saccade, we can turn our heads, and we can move around. These three things allow us to build a picture of the environment that's very high resolution, very seamlessly. We don't even realize that we're doing it. It turns out we're very good at remembering this stuff. I would ask you as the audience here, think back to the home where you lived when you were 10 years old. Can you remember the layout of the rooms? Can you remember where the room was that you went to bed, where your bathroom was, things like that? Think about going shopping. For those of you who have a favorite shopping place, maybe a grocery store or locally, it might be Fry's. Think about, do you know the layout of the store? Do you know where the stuff is that you would want to buy? There's reason to believe that historically people need to know this stuff too. So if you talk to anthropologists about hunter-gatherers, which was humans for the majority of evolutionary time, humans probably had a range of 5 to 10 kilometers. That's how far you could walk in a day. And people were limited by food. So remembering where your food was in the supermarket that was 5 or 10 kilometers in radius was critical. That's what determined whether your tribe was going to live or die. Turns out the memory is even hackable. This spatial memory that people have. Has anyone heard of the method of loci or memory palace technique? So this is the idea of either inventing in your head or remembering a childhood home and placing items in it in order to remember them. So you might be putting people's names in them, but people famously will remember 65,000 digits of pi by placing each digit in a sequence as they walk around a space that they can remember in their head. We enjoy exploration. We go on trips. We get in the car and drive around for fun. It turns out this can be moved onto the screen. So you can take all of the same skills you have and all the same desires and move it onto the computer screen. So some of you may recognize this was Nintendo's first semi-famous video game called Donkey Kong. And the way this video game works is this little character, Mario, who you may have heard of, goes up to the top, dodges all the barrels, and then if he gets to the top, he goes back to the bottom again. It's not a very explorable game. It was medium successful, but not a great hit. But when Nintendo made one small change to the game, maybe not such a small change, and said, well, what if we put the same character in a much bigger world that you can scroll around and explore? Nintendo is now the biggest gaming manufacturer in the world. And this is what really kicked it off. VisiCalc was the first killer app for the microcomputer. It's also the first app for the microcomputer which had scrolling both directions. In fact, probably primarily even, there weren't even very many things that would scroll in one direction at that point. It was important enough that it sold the majority of the Apple IIs that sold in the first few years. And Apple, soon after when it came out with Apple IIe, it made sure to put 4 arrow keys in the 4 cardinal directions rather than just the 2 that it had before. And now there's more going on with VisiCalc, obviously, than scrollability and explorability. There's a lot of interesting stuff. But even people would use it just as a database, it's just as a way to put some information there, and that's definitely taking advantage of scrolling around a bigger space. And of course, today, every single application used on a computer uses the stuff. It's the thing that brought the computer to the rest of us. More recently, we've extended this to also be able to explore scale. So if you look at Google Maps, for example, it was I think the first good example on the web of something that was both scrollable left to right, but also zoomable. And the last point I want to make here at the beginning is that it matters a bit whether you're in the driver's seat or you're watching. If you drive your own car somewhere, you probably have a pretty good idea of where you are and you could drive back, unless you're using GPS. If you like ride in a taxi or something like that, you're less likely to understand where it is you are. So even though you might see the same thing out the window, making the decision to move around makes a difference. So unfortunately, the next few demos I'm going to show you, I'm going to be moving things around, so you're not going to get the full effect. So do try this at home. Please try it out after the talk. Next step of the story brings me to NASA Ames, where a group of us were working with the Mars Exploration Rover. We got so inspired by the panoramic imagery coming back from it that we put together a system with Google's help to let people put ordinary cameras on a pan-tilt device to capture gigapixel panoramas. The GigaPan project has been very successful. There have been over 5,000 devices sold at this point, and over 30 trillion pixels uploaded to the website and shared. Turned out a lot of people were using GigaPan in an interesting way we hadn't really thought of. They were basically making archival information about the world, or even for people who weren't using it for that purpose, other people would take their pictures and use it for that purpose. So for example, the park geologist at Yosemite needs to understand rock slides that happen from the faces of the cliffs in Yosemite. And it's a little bit tricky. When a rock slide happens, you go back and look and say, well, there's a discolored area, that's where it came from. But it might also be where the rock was kind of sliding past. There's a lot of newly white rock, and it's hard to tell which of that was actually coming down. And then the rock that hit the bottom pulverizes, and it's hard to see what's new and what's old. So what he really needed was pictures of exactly that spot zoomed in from before the fall, so you could see what happened. And GigaPan gives him the ability to go back in time this way. He can go back and find any of 100 different panoramas that people take. I guess when you get a panoramic camera, you really want to go to Yosemite and take one of these grand vistas. But he can go back in time in this way. So we thought, well, hey, why don't we run with this? So let me switch over to the Time Machine website. So what we're looking at here is a viewer much like Google Maps or GigaPan, where you can zoom in and see different things. But we can also hit the play button and see it move. So we can zoom in. And what we're looking at here, I have to apologize because I forgot to hook up the wired network. Let's see if I can switch networks in the middle of the demo. So what you're seeing is a record being set in Pittsburgh. Several thousand kayakers are getting together and making the world's largest flotilla. I'm going to switch this. I think we're in the middle of switching networks. Hold on just a moment while I don't want to leave you in suspense here. Hold on. Okay. Okay, and you just saw that the heavens basically opened up. And we're still in the middle of switching that network. Sorry, I just turned off the wireless. So, okay, I think we're on wired now. What you're seeing now is everyone returning all their gear. So that the record was set. There was a lot of question about whether it was going to be set that day because the rain was predicted. But Pittsburghers, being the resolute people they are, went out anyway, even though they all got wet from both sides. Let me show you another image at the time machine site. This is from the Solar Dynamics Observatory. This is a satellite from a NASA satellite. And what we're seeing is a day in the life of the sun. And I've hit play, and from here it's not quite so interesting. I could grab the time slider and go forward and backwards a day. Actually, no, hold on a moment. That'll teach me to switch networks. Okay, let's try it again. Is it going to work better this way? Yeah, there we go. But if we zoom in, you'll see all sorts of things happening at the finer scale. So this is about 500x sped up, the surface of the sun. And we're looking at a ultraviolet band that normally you're not going to see. So that was the moon skipping by just now. But these are basically little mini flares that are going up, and they're following the magnetic lines. And if you look at them, they almost look Newtonian. Some of these look like they're going up in arcs, but then the funny ones over here are going up in this funny diagonal arc and then coming right back where they came from. And that's the magnetic field of the sun talking. But probably the most interesting thing to happen on this day was this very large prominence erupted. So let's grab the time slider and move forward a bit to close to the point where it starts to give way. So it lights up right here. And what's happened is that the magnetic field holding this up has gone unstable. And it was up there for at least a day prior to that. I guess to give you some sense, my little hand that's there, that's a little bit bigger than the Earth. To give you kind of a sense of scale of what's happening. And here, every frame is about 16 million pixels, so it's definitely bigger than fits on the screen, but not a ton bigger. It's definitely zoomable. Let me hit pause here, and let's go to the last time machine I want to show you from the CMU site. This is from a simulation of the universe's evolution from just after the Big Bang to today. What we're not going to see in this simulation is a lot of expansion. That's been factored out. It's as if your camera got bigger alongside the universe. But what we will say when we hit play is that all of the material coalesces together. So under the influence of gravity, it's all coming together. And this is a three-dimensional simulation, and we're taking a two-dimensional projection of that as we're looking. But if we zoom in, what we're going to see at these areas of density where these filaments come together is areas where galaxies are being created. Every frame of this video is about 2 billion pixels. What you're seeing in these clumps are the galaxies. And the simulation is not quite big enough to have billions of stars in a galaxy. It's more like hundreds of stars in a galaxy. But it still has a lot of the same features that we see in the universe today. And one of the reasons that this particular time machine is important is it illustrates why you might want to use this sort of approach when you're doing scientific research. So one of the puzzles in putting together simulations of the universe was, in fact, looking through Hubble at the history of the universe is why do black holes form earlier than kind of simple models might predict? And it was a tricky thing. It was hard to explain how the material could get cold quickly enough to condense into the black holes. And it turns out that by looking at this time machine, the researchers were able to figure out the answer to the question. And the answer to the question basically is that all of the material, instead of radially symmetric around these center parts, they turn into filaments. And the filaments are really great at A, dissipating all their heat. It's a good shape for dissipating heat. And B, it's really great for then turning into a train, piling into where the black hole is going to form, because it doesn't have much surface area to push back against it. It's the sort of thing that it's hard to discover by running lots of numerical analyses of like your huge three-dimensional data set, but you can see it in an instant. Back to the presentation here. So the time machine, the idea is you could capture in lots of different ways. You can capture with a camera, you can capture with a camera doing pan and tilt and mosaic, but we could also do satellite imagery, which is what I'll get to very soon. Depending on the images coming in, we might have to align them over space, like if we're mosaicing, align them over time, if it's a camera that's out of alignment. So that there's some tricks there. What we're doing to be able to then take this interactive, very high-resolution video and stream it to a web browser is we're turning this massive video into many smaller video tiles. So in much the same way that the Google Maps might divide static images into a quad tree of little tiles, we're doing something similar with videos. It's not exactly the same. The tiles, the sibling tiles actually overlap with each other. So when we switch between tiles, we're switching between overlapping tiles. Right now, when we're serving videos, we basically compile it all up statically, and then there's no computation happening at serving time. So it scales very nicely. The viewer is HTML5, and it's basically taking advantage of the programmability of the video tag in HTML in the same way that Google Maps, for example, takes advantage of the programmability of the image tag. So I want to switch gears and talk about Google Earth Engine. I see Rebecca Moore in the audience. She's the lead for Google Earth Engine. Google Earth Engine is a planetary scale platform for satellite data and analysis. And it's basically a way to take the incredible collection of scientific imagery from Landsat, MODIS, and a number of other scientific satellites, bring it all into one place and be able to run algorithms against it. And it's a magical thing. So Google Earth Engine, for example, has more Landsat satellite data on spinning disk here at Google than anywhere else in the world. By taking algorithms that traditionally researchers have had to say, well, let's see what I can afford to store, and let's start downloading from USGS, and a month later I start to work on kind of my corner of the world. Now those researchers can take the algorithm and immediately see that algorithm applied everywhere. So not only can they see, is it valid for the place that you're looking at, but they can look for, what are other places in the world that are similar? What are the places that are different? Let's try to understand how different parts of the world can inform that. The scale is massive. I mean, it's petabytes and petabytes of data. So we were excited, talking to the Earth Engine folks. Maybe there's some way we can work together. So there are lots of applications today Earth Engine is being put to, including detecting deforestation, trying to model carbon input and output to in the biosphere. So the good news is we talked about it and we got excited and we decided to do it. So starting in December, I came on board here, and a few folks from CMU were also on board to help out. And with a lot of help from the Earth Engine team, we put together a release just this past Monday. So I want to show that to you now. So this is the brand new Earth Engine site. And what I'm going to show you is I'm going to show you the public site. So there's also a private site that scientists that are in the what we call the Trusted Tester program can access, that gives them a lot more controls than what you're going to see here. But this is what's being exposed to the public right now. So I'm going to click here, and what we're going to look at, actually I'm going to switch. I'm going to change the order up just a little bit here. I'm going to go instead to the lower resolution of our 2 videos. So this video is about 6 billion pixels per frame. And when I hit play, what you're going to see is the seasonality of the Earth over about 11 years. This is recorded from the twin MODIS satellites that are orbiting the Earth each day. So we're getting daily pictures, which are then compiled and cloud removed over roughly 16-day periods. And when we zoom in, we can see all sorts of amazing changes happening on the planet. So I've zoomed into the Aral Sea. The Aral Sea at one time used to be this big. And what we're seeing is it drying up. So you can see in 2009, it just about, this lobe is done. Now since then they've had some more rain and it filled up some. But basically the story of the Aral Sea is the story of this little area of land over here and this area of land over here. The water that was going to the Aral Sea is now growing plants. Some of the challenge of so we've just looped back to 2000 now, but some of the challenge of the Aral Sea drying up in this way is that you have all of the substances that were going into the sea, such as pesticides, a lot of the salts and things like that, becoming powder and airborne and causing a number of problems. And of course, there's fisheries and things like that, which were completely devastated. Let me show you another spot on the seasonal video. These are the sub-Saharan grasslands. And what you'll see is every season we turn from green to brown. Let me zoom into Lake Chad here. Lake Chad used to be full all the time, but right now it's basically seasonally filling up. And you can see each summer it comes and fills up like this. You can see it come from the bottom up to the top. Some years it doesn't fill up quite as much as the others. But another really interesting effect you can see, and this one's a little harder to see, but as I zoom in here and we watch it turn from green to brown, look for little freckles appear. Little brown areas that appear and kind of fade out. These are man-made set fires to manage the grasslands. And you can see those from space. So let me switch gears and move to the larger of the 2 time-lapse videos. This one is compiled from Landsat, and instead of being seasonal, what we're going to see is an annual animation, each pixel of which is 30 meters. This makes a video that's 1.3 million pixels on a side for a total of about 1.8 trillion pixels. So it's 1.8 terapixels per frame. So this one animation has as many pixels as has been uploaded to the GigaPan site since it started. So let me zoom in, and let's go look at some interesting stuff here. So I'm going to zoom into Lake Mead, and just to the left of Lake Mead, we're going to find one of the fastest growing cities over the past 20 years in the US. This is Las Vegas. And what you'll see from zoomed out like this is you'll see that we have this combination of Vegas becoming bigger and Lake Mead becoming smaller. So it turns out that it wasn't necessarily because Las Vegas was using more water, but rather that they were having less rainfall. But there are real water challenges in this area, of course, because all the water is being brought in from other places. Let's zoom in a bit more, and you can see kind of the actual resolution of what's captured by Landsat. Next place I'd like to take you to is also in the US. I'm going to take you to West Virginia. And in West Virginia, if you zoom in different places, what you'll find are these funny little areas that it spanned over time. And these are huge. So we're looking at things that are many hundreds of meters across here. This is called mountaintop removal. And what you're seeing is a mining process whereby the tops of mountains are being taken off, sifted through, and being placed into the valleys. As we zoom out, you'll see that there's a lot of it going on. Let me zoom out even further. And the scale of what's happening, the first time I saw it, just floored me. Each one of these little tiny spots is several 100-meter mining operation. And the final thing I'd like to show you with the video here is in the Amazon. And this video only goes back about 13 years right now. But even in the past 13 years, there's a lot to see. So there's a lot of this area here, which is kind of spotty, that used to be forest and isn't anymore. But if we zoom in further and look at the areas around the roads, what we'll see is the process of that happening. So we're cycling over and over from 1999 to 2011. You remember this is so I'm not even zoomed in all the way right now. So you can see the little tiny roads here. So each one of these spots is a fairly massive farm. So the Amazon is largely being turned into land to graze cattle and farming. So that's the end of the demo. I want to switch back to the rest of the presentation, if I may. So let me briefly address some of the lessons that we've learned both on Time Machine prior to coming to Google, but also working with Google here on the Earth Engine team. Working with Earth Engine team has been wonderful, truly wonderful. The people are incredibly intelligent, incredibly helpful. I've learned a ton coming here, and I can't believe what we've been able to accomplish in such a short time. There's a ton to learn here at Google, without a doubt. There's no comparison between the resources that I have access to here at Google and what I've had access to at CMU, so I'll just kind of not talk about that. Other lessons. It turns out to be very important, this connection between when the user drags the mouse or zooms in, you want to see a response right away. You don't want to see a 1-second round trip to the server. You really have to do work to, in the same way that with a video you would buffer temporally, we need to buffer spatially. So we're buffering pixels around what you're looking at. So when you pan and zoom, we have those pixels all ready to go, and we don't have to do a round trip to the server. You want to minimize the time to first pixel. What does that mean? It means if you suddenly have the idea, I need to see what the Amazon looked like in 1993, you want to be able to link right into that. You don't want to spend like 5 minutes downloading an application. You don't want to spend a month downloading Landsat data. You want to be able to get right to it. And that's critical for making connections between fields. If there's a huge barrier to looking at information, you're only going to look in the places where you know you're going to find something. And if we're always just looking at the places where you know you're going to find something, we're not going to make the interesting discoveries. Deep linking, being able to connect to these things in the web. So both of these points kind of talk to why would you do it on the web when it's a little harder to do on the web, but there are really good reasons to do it, and the deep linking is one of them. So you can connect what you're seeing in these animations to other forms of information. Other lessons. Efficiently accessing essentially 3-dimensional or perhaps 4-dimensional data when you have lots of bands from what's inherently a 1-dimensional spinning media storage is a real challenge. So it's probably most of the scaling issues we ran into were around that, and that's true across the scaling from the CMU down 1 and 10 and 100 machines all the way up to the thousands of machines. The access patterns for this sort of big data don't tend to lend themselves to caching very well. You end up asking for funny slices through the data across all of the data. If you ask for all the data, it's easy. You can just grab it all in linear order and you're fine. If you're asking for little pieces of the data, maybe driven by a person, that's cacheable. But if you're asking for some funny slice across everything that's sparse, it can be very hard. So what do? Do you make lots of different ways of storing your data on disk, and then you have a problem at write time? There are lots of problems there. But everything's going to change someday when SSD becomes as cheap as spinning media. That'll change all the rules. And last lesson I want to share with you is that Google discipline is required at the mini cafeterias and snack areas. I made an inadvertent experiment on myself, unplanned experiment, and with very high confidence, I put on weight when I'm here. So next steps on the time machine side. One of the things that we know we need to be able to do is temporally subsample. So what do I mean by that? So spatially subsample lets you zoom in and out in space. Temporally subsample lets you go through orders of magnitude difference in time progression. And you may think, well, that's silly. I mean, that's as easy as spatial. It turns out it is not true. In most domains, what is salient at different temporal rates is very different. So for example, in satellite imagery, if you're looking at satellite imagery over the minutes to hours, what you're seeing is weather patterns. You're seeing the clouds moving here and there. When you start to speed that up, to looking at a day every second, suddenly the clouds don't make sense anymore. The clouds are just moving around too fast to make sense. And what you probably want to be doing is looking at the ground. You keep speeding up, and you see something like the seasonal animation we saw. And that seasonal animation would be completely gibberish if we still had the clouds in it. You go further still, and looking at the decadal changes in the Amazon is confusing with the seasons. In fact, the RLC is a little bit confusing because you kept seeing kind of the seasonal cycling, but what you really want to do is you want to compare like July against July against July. So as you start to speed up, different things become salient. So another change that we would like to be making to the time machine infrastructure is the ability to build these sorts of explorable animations real time on the fly. Right now we're building everything in batch mode, which has some advantages. It has the scaling advantages I mentioned earlier. And it makes sense for like big data products like we saw today, where one data product makes sense for a lot of people. But if you're a scientist working on one particular data product and there aren't a lot of people seeing it, you may not want to wait in batch mode for everything to compute. And in fact, there are lots of really interesting things you want to do, even general purpose. So there are specific calculations you might do for satellite imagery, but then there are even these general purpose real-time calculations you might want to do. In the same way that analyzing or trying to understand static imagery, you might do a contrast stretch. You might try to adjust the dynamic range of what you're looking at to match the dynamic range of your eyes so you can perceive some particular part of the image. The same is true of videos. So you may want to be able to take what's in the video and amplify tone changes over time. You might want to amplify motion. So if there's a little bit of motion you can't quite see, let's turn up the knob. And these are interesting sorts of calculations that we'd like to be able to do, that we think will generalize across all the different data sets. So that's the end of my talk. I'm interested if you have any questions. Yes.
Sure. Okay. This was really cool. You told some really interesting stories with the data, and so I had a question about what are the hard problems in that regard, in selecting and communicating such stories from the giant data sets that you have.
So for collecting and kind of communicating the stories, it's an interesting thing. And in fact, in the demo is I kind of skipped past an introductory video. One of the things that we've set up is the ability to script a tour through the world, so to speak. So in the same way I was standing in front of you, kind of in real time showing you, we can script an expert, someone who knows more than I do about the data and telling a story, and we can then render that to a video. An interesting thing about rendering it to a video is we still have the meta information. So at any point when you're watching this video, you can break out and explore on your own, and then you can go back. So in fact, if you go to the earthengine.google.org, you'll find that experience, exactly what I'm saying.
In the early part of your talk, you mentioned the mnemonic mechanism using space to remember things. And then you went on to the time series part. I didn't quite see the connection between the two. I find the first thing absolutely fascinating, that you can remember thousands of digits of pi and so on. And I've been interested in other methods like the major system and so on. So is there a connection?
So the connection for me is really in this explorable space. So it's connecting the ability to explore and understand a space that might be 1 billion pixels or 1 trillion pixels. So connecting that to video, I think, makes it for a very interesting, certainly we're finding there are a lot of things you can do with it. So I think that it's the thing that we're doing that YouTube doesn't, right? It's the ability to go and find nooks and crannies and go and explore.
Thank you, Randy.
Thanks.